All right. This OneNote page is visible to you, I guess. So welcome to the first tutorial of this course, Quantum Mechanics. As you already know that we have an assignment for this week, and we have some assignment problems. Basically, 10 problems we have, and will be that will be based on this week's content of the course, I guess, and we'll be solving these problems together. Mainly, I'll be starting on solving it and discussing with you. So, if you have doubt at any point, you can unmute and ask me. And if you have already solved it, you can cross check whether that is matched with this solution or not. Or if I make some mistake at some point, you can also correct me. Alright, let me take my pen. Right, um, hmm. So the first question is, this is basically a quantum mechanical eigenvalue and eigenfunction sort of a problem, right? So where the energy eigenvalue, just the energy eigenvalue and the corresponding eigenfunction for a particle of mass m in one-dimensional potential Vx is given to you. So you have a problem where you have a particle of mass m, and that particle is actually experiencing a potential which is also one-dimensional. That is the x you can see, because that is the simplest case to solve a problem one-dimensional. And in presence of this Vx potential, you are asked to you have this information that the particle can have this eigenfunction like this, and the energy eigenvalue means you know that the eigenvalue energy means it is the eigenvalue of the Hamiltonian operator mainly on this eigenfunction psi x, right? So now this psi x has an unknown positive constant a, right? And you have to find out what is the potential that is involved when you get this kind of a solution of eigenvalue and eigenfunction. So the basic idea should be clear to you that whenever you have been given this kind of a problem, you know that you have to straightforward go to the Schrodinger's equation to solve this, right? Because there you have this Hamiltonian and this eigenvalue and eigenfunction terms involved with the potential as well. So we'll be doing that. Now let me just go to a blank page and start doing this. Okay, so just 1 second, someone else has also entered. Right, so we have just started our tutorial. So I was on the first problem itself. Okay, so um, it is again very thick. Yeah. So as I was discussing that whenever you have such a problem that you have been given the information about the energy eigenfunction, energy eigenvalue and the particle eigenfunction or wave function, and you have the information about the potential Vx, you know that all these is commonly connected to the Schrodinger's equation, right? So you have this psi x, which is your eigenfunction, you have this E, which is your eigenvalue, and you have this information on the one-dimensional potential Vx. So you know the common link to all of them. So use Schrodinger's equation, right? So Schrodinger equation, what does it tell you is that if this is a Hamiltonian operator H psi, that is equal to E psi. What does it mean? So this is the Hamiltonian, means this is the operator. So which actually means that it will give you the energy eigenvalue if you operate this operator on a wave function or eigenfunction of this operator, that is psi x, right? So basically you have in Schrodinger's equation, you know this operator form of Hamiltonian, which is minus h cut squared by twice m So I'll assume that you have followed this lecture, so I'll just directly jump to this equation that is already known to us, and not explaining it why it is coming. So sorry, let me just separately write down the operator first, and then I'll, yeah. So it will be minus h cut square by twice m. This is the kinetic energy term basically, and the second term will be the potential energy term, or the potential term Vx operated on psi x. That will be equal to E psi x, right? Now, so you have minus h cut square by twice m. So I forgot to add this d2 dx to here. So we have this operator has this double derivative on x here. So this d2 dx will operate on psi x. So it will give you d2 psi dx2 plus vx psi x. Now, if you remember the problem that is given to you, they have clearly mentioned that your energy eigenvalue is 0, right? So you put E equal to 0 into psi x will give you 0 only. So the right hand side becomes simpler, it is equal to 0. So it actually simplifies the problem even more. Now if you look at the function of psi x, that is the functional form that is given to you in the problem, is a by x squared plus a squared, where a is some unknown constant given that a is positive. I think that is mentioned in the problem that a is positive. So basically, so you have to use this information here. So you have to take a double derivative on psi with respect to x. That means first take a single derivative d psi dx, right? So you know how to take derivatives. So I'll just write down. Just cross check whether I'm making a mistake at any calculation. So this derivative you can know from here, and so basically this is simple to do, I guess. So you know that you can assume y equal to x squared plus a squared, and then you can take d psi dx equal to just partial differential sort of d psi dy into dy dx. Then you simplify, this is d dy by of a by y into dy dx becomes 2x, right? So this is minus a by y squared 2x, and y squared is minus 2ax by x squared plus a squared whole squared. Okay, so I hope this is clear already. Now the double derivative d2 psi dx2 if you have to take, so you have to basically work on this and take another derivative d dx, right? So this is d dx of minus 2ax by x squared plus a squared whole squared. So you take this 2a common. So your derivative on x, someone else has joined. Okay, so we are kind of in the middle of solving this problem number 1 in this tutorial. So let us continue. So I was taking the second order derivative on psi, so to get d2 psi by dx2. So that is, so as continuing, minus 2a. Then you first take the derivative on x, so this is 1 by x squared plus a squared whole squared, and then you take also the derivative on x squared plus this term. So this becomes minus 4x squared by x squared plus a squared whole cube, right? So if you simplify and gather all terms together, so you will get a term like, just cross check for yourself, do this calculation yourself and see if you get this. So 2a 3x squared minus a squared divided by x squared plus a squared whole cube. Now we have all the information that we need here, right? So now we'll put together all the terms together, and then we see that whether our problem is just one second, let me go full screen. Yeah, so I think now it will be better. Okay, so we have now gathered all the terms together, so we'll be just simply putting it together. So from here, this was our last thing, and we are calculating this term, right? So we can directly jump to this. Now you have this value minus h cut square by twice m. You know d2 psi dx2 is into 2a, 3x squared minus a squared divided by x squared plus a squared whole cube, plus vx into psi x value is already given, so a by x squared plus a squared. Now the right hand side is 0, right? So you take vx to one side and put all the terms to the other side. So this minus becomes plus going to the other side. So this is h cut squared 3x squared minus a squared. This 2 and 2 cancels out, and this a and this a basically cancel out together when you take this term to the other side. So this is x squared plus a squared whole cube, and this vx also has this x squared plus a squared divided by, so it gets multiplied on the other side. So finally you get vx equal to h cut squared 3x squared minus a squared divided by, sorry I missed one m, so this m will be in the denominator. So this is m squared plus a squared whole squared, right? So this is our solution to the first problem. This is our answer, that this is the one dimensional potential value that the particle will be experiencing if it has to satisfy that its eigenvalue, energy eigenvalue is 0 and the eigenfunction looks like this term given by them, right? So I hope, so this is done. So we can choose the correct answer from here. Here already you can see the correct answer is A, so we have got A exactly, right? Now move on to the question number 2. So here it's said that consider a photon that scatters from an electron at rest. If the photon scatters at an angle 60 degree with a wavelength lambda prime, that is twice its incident wavelength lambda, then the angle at which the electron recoils will be how much degree? So first of all you have to identify what problem it is you are dealing with. So once you see that there is a photon that is scattering an electron at rest, you know that this is a typical Compton scattering problem, right? So Compton scattering experiment had this thing that the electron is sitting at rest and a photon is incident with some incident wavelength. In this case, the incident wavelength we let's say mark by lambda I. Lambda I means lambda incident, and in this problem the lambda incident is given as a value of lambda, and it is getting scattered from the electron and getting scattered with a different wavelength, which is let's say the final wavelength lambda f, and in this problem lambda f is denoted by lambda prime, and it is also mentioned that lambda prime is twice of incident lambda, that means 2 lambda, right? And so because obviously the electron will also experience a collision with the photon, so it will also have a recoil velocity, it will also move from its position with an angle to the original like plane of axis. So that angle you have to, that recoil angle you have to calculate here. And similarly when the photon scatters, it will also deviate from its path by an angle. This angle we call phi. Here phi is already given 60 degree, and let's say the recoil angle of electron is let's say theta, but theta is unknown and you have to solve for theta using the other information that is given to you. So let us, as I said, that you have to solve it by the Compton scattering problem method. So we'll be doing that. So question number 2 is based on Compton scattering. So it's always helpful to remember or like understand these things in terms of diagrams. So Compton scattering has a very nice diagram, which will actually, if you remember the diagram, you will not be needing to remember the mathematical equations really. So that is very helpful. So we'll be drawing that diagram and then write down the relevant equations to us, right? So this is, let's say, our electron which is at rest. That means it has no momentum, no velocity at all here. Okay, and there comes a photon. For the photon I am drawing it as a wave like this, so wave packet like. So this is a photon with a incident wavelength of lambda I. So I am drawing first in a generalized notion. So lambda I is a general uh, notion for the incident wavelength of the photon. Okay, and after it gets scattered from the electron, so let's say this was the original direction of motion of the photon, so from its direction it will be scattered off to some different direction with an angle, right? So let's say this is the direction that it scatters off to. So this is the angle that it makes while scattering off, right? So this angle, generalized notion, is phi, let's say, for our case. And the final wavelength is actually different from the incident wavelength. So this is the final wavelength of the scattered photon. And because the electron has also experienced this collision, so it will have a recoil momentum, and because of that momentum it will recoil with some directional or some angle deviation theta from this plane. So theta is the recoil angle electron. Okay, so this is the electron, let's say it has gone this way, and because now it has gotten a recoil, so it will generally have a momentum or velocity. Right now, earlier its momentum was 0. Okay, and now it has a momentum which we denote as PE, momentum of electron. And because it is considered, because it is a quantum mechanical thing, so you will have to consider the relativistic energy expression of electron. So you know that by relativistic energy I mean, sorry, this is L, so this is second is T. Relativistic energy, E means E equal to root over of P squared C squared plus m naught squared C to the power 4. So where you consider the velocity of light in consideration, and so basically here P is the momentum, C is the velocity of light, m is the rest mass of the object, in this case electron. So rest mass means when the object is at rest it will have a mass that is m naught, right? But when the object is at motion, its mass will not be same as m naught. So that is the relativistic idea. Anyway, so for our information, for our purpose, this will serve our purpose. So this relation, energy is equal to this thing. So from this case, initially when the momentum was 0, the electron at rest. Okay, so then its mass me is equal to basically the rest mass. Okay, as far as I remember, electron's rest mass is a standard of 0.5. Rest mass energy, basically, if you try to say 0.5 MeV is the rest mass energy equivalent. So this is not the, you can see say this is the rest mass equivalent energy. That means this is m naught C squared. Okay, anyway, we'll not go into that. So, and when the electron is at motion, when it has gotten some recoil velocity, so then its momentum not equal to 0, but now the momentum has become PE. So you can back calculate PE from here. So PE is basically E squared minus m naught squared C to the power of 4, right, divided by m naught squared C to the power 4 divided by C squared, and the whole thing is under a square root. So this is root over E squared minus rest mass squared c to the power 4 by c. This is the recoil momentum that the electron has obtained now after the collision with the photon. So now, these are the basic information that we will be needing, and these angles are theta and phi. So I will directly jump to the mathematical formulation now, because I'll assume again that these are things that are covered in the lecture. So if you have not, just go back and check. And as I said, it is very easy to actually get the mathematical expressions once you have this diagram clear. So it is nothing but the energy and momentum conservation relations that you need to use, that x and y direction, if this is your x direction and this is your y direction, on both of the axes independently you have to like conserve momentum, total momentum, like before and after momentum you have to conserve, and the energy, it is direction independent, so that there the total energy conservation you also have to use. So after you use all those things, so we'll get this kind of equation of Compton scattering, that lambda f minus lambda I, that is delta lambda, which is the wavelength shift that the photon experiences after it gets scattered by the electron. So this is delta lambda is equal to h by m naught c into 1 minus cos phi. So this is the main mathematical equation of Compton scattering, and this term actually has an official name, that this is called the Compton shift. Compton shift is nothing but the wavelength shift that the photon experiences after it gets scattered or Compton scattered from the electron, right? So this is the idea, and this phi is the scattering angle of the photon. Okay, now let us look at the point of view from this problem, that in this problem they have given us phi equal to 60 degree, and lambda f is equal to lambda prime equal to 2 lambda, and lambda I equal to lambda. H, m naught, c all are standard constants, so those values are already known. But you don't have the idea about theta. So theta is how much? So to get theta, we will have to basically look at the different like energy and momentum conservation that gives us some equations. That equations will be relevant. So first of all, if you use the momentum conservation, okay, along x-axis. So the total momentum before collision and total momentum after collision along the x-axis is, so initially this whole momentum of the photon is basically h by lambda, p equal to h by lambda, you know momentum formula. So this is h by lambda I, pi equal to, and this is entirely along x-axis, right? And after, electron has a momentum 0 because it is at rest. This is before collision, and after the scattering or collision you will get, this has two directional components. So one is, because it has an angle, so it will have an x directional component and an y directional component. So let me use a different color here. So if you now divide the components from this angle, so the resultant thing along the x direction, so first of all, the scattered photon has an wavelength pf is equal to h by lambda f, right? Now this h by lambda f has an angle phi with x-axis, so it will have h by lambda f cos phi is the x directional component of this momentum from the photon, and from the electron also you have pe along this direction with an angle theta, so it will also contribute along x as pe cos theta. So this is the net momentum component after the collision along x-axis. Okay, and what will be the y-axis components? So basically this electron will have a pe sin theta over here along positive y direction, and the photon will have a y component but in the other direction, that is in the negative y direction, because you see that this angle will give a negative component along negative y directional component. So if you take that into consideration, so it will have a minus h by lambda f sine phi. This is along y cap and this is along x cap. And you see that before the collision there was nothing in the y direction because everything in the x direction only. Okay, y direction this is 0. So now you have this idea that we'll need to be using here. So along x-axis, as I said, that the momentum conservation gives you h by lambda I plus 0 from the electron is h by lambda f cos phi plus p cos theta. And from the y-axis direction, if you compare, so initially y-axis has 0 momentum contribution, and after the collision it has h by lambda f sin phi plus p sin theta. So these two will be, let's say, Roman 1 and Roman 2. These two will be relevant to us. So you quickly take sin theta and cos theta to the other one side. So you have basically P cos theta from 1 is equal to h by lambda I minus h by lambda f cos phi. And you have Pe sin theta from 2 is equal to h by lambda f sin phi. Now you divide both of them. So basically you take divide this divided by this. So you'll have a P and P cancelling out and you will get a tan theta. So if this is your 3 and this is your 4, then you get 4 by 3 is giving you tan theta is equal to h by lambda f sin phi divided by h by lambda I minus h by lambda f cos phi. Sorry, this is not theta, this is phi. So you take h by lambda f below, so this is sin phi. This divided by h by lambda s is basically lambda f by lambda I minus this cancels out, this is only cos phi, right? So now you have an equation or a relation that is giving you theta somehow, because theta is what they are asking in the question. So roughly theta is tan inverse of, so this is the final formula of theta. I could have directly written down the formula itself, but it is better that because it is not possible to like just remember and like memorize all the formula like this. So it is better that you sometimes for quick solution it is better that you remember them, then it will save time. But otherwise this kind of an approach will be helpful whenever you don't memorize the formula and you have to calculate. So this is the theta, right? So now you have the information on your with you, so you put them. So sin phi is sin 60 degree, lambda f by lambda is equal to basically lambda prime by lambda, which is twice, that means it is 2 minus cos 60 degree. So this is tan inverse of sin theta sin 60 degrees root over 3 by 2 divided by 2 minus cos 60 degrees half. This is tan inverse root 2 by 2 divided by 3 by 2. So this is tan inverse of 1 by root over 3, which you know is 30 degree. So you get that theta, that the recoil angle of electron, that is the answer to this problem number 2 is 30 degree. So we mark this in this here. So theta is the correct answer is 30 degree. Right, so this is done. Now problem number 3, we go for this. So problem number 3 is that for a particle in a one-dimensional box, the ground state energy is given by E naught. So the allowed energies for such a particle will be what options are correct out of these 4 options. So this is the common problem of quantum mechanical 1D box, or also called as infinite potential well problem. And so basically it is very simple. There is a standard formula for the energy eigenvalue for this kind of a problem. So we'll be directly using that. I'll not be starting to solve the whole 1D box problem, because again that is covered in the lecture. Okay, so let us do that directly, writing down the. Now this formula is something that you actually need to memorize, and you will anyway memorize once you do it, like, because it is a very common problem and a very common formula that you have to use everywhere. So also called as infinite potential well. So anyway you will memorize that, because that will be quickly implemented when you are solving this kind of problem all the time. So basic diagram is this. I prefer to draw a diagram at every stage, right? So this is the potential box or a 1D box like this, where the boundary of the box is sitting at infinite potential. So from this boundary, from both sides, the potential is so infinity, and inside this 0 to L, which is the size of the box, the V equal to 0, the potential is 0. So the particle naturally, because the potential is infinity, so it will not be able to go outside or tunnel or something, so it will be constrained to move in this extent only, this box, right? So V equal to 0. So it's like V equal to 0 between 0 to L, and V equal to infinity at all the other positions. So for this kind of a system, you have this now eigenfunctions. Okay, someone has joined, just let me. Okay, so actually we are already in middle of solving this assignment, so I'll continue where I am at. So currently I am solving this, we are solving this question number 3 of 1D box of particle in a box problem. So I was trying to draw the energy eigenvalues for this kind of a problem, because this is 1D, so it is easier, it has only one direction x, then it can also be visualized in 2D and 3D with more complexity. But for starters, that problems are also there in the assignment, you must have seen it, but for starters we first start with 1D. So the different energy eigenfunctions for this kind of a problem is En equal to n squared pi squared each cut squared divided by 2ml squared, where L is the size of the box. Okay, okay, and n is a quantum mechanical number which can only take integer values like 1, 2, 3, etc. Okay, this is your energy eigenvalue for one dimensional box problem. N can take values 1, 2, 3, so generally, very naturally, n equal to 1 is your ground state, right? N equal to 1 is the ground state, and which is in this problem given as ground state energy is E naught. So E naught will be n squared is 1 squared, so 1 pi square each cut square by 2 ml square. That is given in the problem, that E naught is the ground state energy and E naught is will be this value. So if that is true, then naturally En, which is the general form of the energy eigenvalue, is n square times this whole thing that is in the bracket is actually nothing but your E naught. So this is a very useful and simplified form that you can write down for this particular case, where they have mentioned that E naught, the ground state energy, is this. So all the other excited state energies can be written down as n squared times E naught, where n is the quantum mechanical number that signifies what state you are at. Whether you are at ground state, then n is 1, then En is simply E0. Okay, if n is 1 and you are at GS or ground state, then En is simply nothing but E naught. But if n is greater than 1, that means any excited state, right? It is not a ground state, excited state, then En will be that state's quantum mechanical index n squared times E naught, right? Now this makes your life very simple for solving this problem at least. So if n equal to 2, for the next step on n equal to 1 will be n equal to 2, which is the first excited state. That will give you E2 is equal to 2 squared E naught, which is 4 E naught. Similarly, the next excited state is the second excited state, basically after ground state, is n equal to 3, where E3 is equal to 3 squared E naught is equal to 9 E naught. And like this you will get the other state as E naught, 4 E naught, 9 E naught, then 4 squared will be 16 E naught, and like this. These are the quantum mechanically allowed energy state for the particle it can be in case of this 1D box problem. So we check what options are given in the problem that matches with these values, and what does not match, that will not be allowed energy for this problem. So you can see naturally you have 2 E naught, which is not an energy eigenvalue, 4 E naught is an energy eigenvalue, 6 E naught is incorrect, and 9 E naught is an energy eigenvalue. So the correct answer will be B and D both. This is true, that those are the allowed energies for this case out of these 4 options. Now move on to question number 4, that consider a particle in a two-dimensional box where ground state energy is epsilon naught. So just take a look that the earlier problem was 1D box problem, and now you have 2D box problem, which is nothing but the two-dimensional version of the earlier problem. So both are connected, you will see. So in a 2D box, the ground state energy is now given as epsilon naught. Then the energy E equal to 13 times epsilon naught is twofold degenerate. That is true or false, you have to check. So first of all, you have to write down the energy eigenvalue expression for this 2D box problem. From there you have to calculate what is the ground state energy, that is equal to this expression of E epsilon naught, and from there you will see what is this exact value of capital E, whether it is twofold degenerate or not. So first of all, twofold degenerate, if you understand or not, degenerate means that when you have multiple states, okay, when you have multiple states that are different from each other, eigenstates, but they have the same eigenenergy, means you have different psi1, psi2, psi3, all are independent of each other, different levels, but all of them have the same energy, let's say E for example, then that will be, they will be called degenerate. When it is said that it is twofold degenerate, that means there exists two such states, psi1 and psi2, let's say for example, who both of those have the same eigenvalue E. If that is, there are three states that have the same eigenvalue, then the energy will be called threefold degenerate. But for E, here they are saying that it is twofold degenerate, means there are two states possible which can acquire the same energy independently. So as I said, we'll be using the 2D potential box or 2D particle in a box problem, which is a further dimensional extension of the 1D box problem. So 2D particle in a box. So basically the idea is that in 1D case you assume that you have this x direction where the particle has a potential 0 between x equal to 0 to L, because the box is one dimensional size 0 to L, and all other positions v equal to infinity. So the particle cannot exist there. For 2D box, you just assume the box is itself 2D, okay, and it is a square box, so both of sizes, length and width is equal, L and L, right? And V, the particle potential that the particle faces, equal to 0, or Vy equal to 0 when x is between 0 to L and y is between 0 to L. So let's say the two dimensions you are talking about are x and y. So these are the conditions that in these boundary Vx and Vy, the potential that is faces is 0, and all other positions V equal to infinity. Okay. So for our case, we'll be needing the eigenvalue. So you can try deriving it from the idea of 1D problem itself. But for our case, we'll be needing the expression of the energy eigenvalues. So which is very simple. If you derive, you'll see that it is nothing but the total eigenvalue in this case is nothing but the individual um, eigenvalues. That means if you take x-axis as an independent 1D box and y-axis box as an independent 1D box, so both of their combined eigenvalues will be giving you the net eigenvalue. So En is the net 2D box eigenvalue and En1 is the 1D box eigenvalue when you consider only one direction. Okay, let's say this is x directional box eigenvalue, and let's say the second one is y directional 1D box eigenvalue, right? And basically your total potential then becomes Vx plus Vy, and you have the eigenfunctions will be psi nx for Vx and psi ny for Vy, and that entire net psi xy will be a product of psi nx, psi ny. Anyway, so basically this is the thing that we'll be needing, right? So total energy expression eigenvalue En equal to, you know that this is standard n square pi square h cut square by 2m L square. This is for x direction, and for y direction case also, because it is a square box, so it is again L. Only the quantum number identifying it will be different, n2. So n2 squared pi squared h cut squared. So by simplifying you will get that this is pi square h cut squared by 2m L squared n1 squared plus n2 squared is equal to En. So you can simplify En because it is a box problem. So you can simplify that this is n squared pi squared h cut squared by 2m L squared. So by comparing we see that this is equal to this from this relation, that is n squared, the net quantum mechanical number to identify the energy levels of the particle in a 2D box, is a linear combination, is squared is a linear combination of individual 1D boxes number squared. That means n squared equal to n1 squared plus n2 squared. So this is something that will be needing to use. Now in the question it is given that the ground state is epsilon naught. So if you have two directions x and y, so what will be the ground state? So the simple idea is that, so what are the values that n1 and n2 can take? So let us make a chart, right? Let us make a chart that what are the respective values of n1 and n2, and in term based on that what will be n, because n is related to them by this equation. So for ground state, that means the minimum state it can be at, you know that n starts from 1 generally, right? So n1 also starts from 1, 2, 3 dot dot dot, and n2 also can take values of 1, 2, 3 dot dot. So the lowest possible energy, both of them will be n1 corresponding to n1 equal to 1 and n2 also equal to 1, because n cannot be 0, right? And you have to choose the lowest. So both of them 1, then n squared is yeah, so basically we write down n squared here for our convenience, because that is a relation, right? So n squared is 1 squared plus 1 squared equal to 2, right? So the ground state energy in this case will be 2. So let's say this is the, so I am writing down it in the other way round, but let us just understand that I am meaning to say that first you get n1 and n2, then you calculate n squared, and then you get En, which is nothing but n squared pi squared h cut squared by 2m L squared. So here, because n squared is 2, this is 2 pi squared h cut squared by 2m L squared. Now in the question it is given that ground state energy is epsilon naught, which we have just calculated that it is pi squared h cut squared. If you cancel out the 2, this is actually 2 pi squared h cut squared by 2m L squared. Now in the question it is also given that there is an energy E equal to 13 times epsilon naught, which is nothing but 13 into 2, that means it is 26 pi squared h cut squared by 2m L squared. Now you know that En, if you generalize it with the En version, that is n squared pi squared h cut squared divided by 2m L squared. You have to use a general formula because you don't know what level this energy corresponds to. So if you compare it with this, the general formula, then this part is common. So you are left with this n squared is 26. That means n squared equal to 26 is somehow you have to hold true for energy to occupy this, to obtain this value. So how n squared will be 26, at what combination of n1 square and n2 squared? So you have to find out a combination where always n1 squared plus n2 squared will be 26. So just it is easy to actually get the combinations because you know what are the prospective values of n1 and n2. So naturally, because you have 26, you have to go for a nearest like square term what gives closest value to 26. Just first thing that comes to our mind is 25, right? 25 is 5 squared. So basically if one of this n1 and n2 is 5, then you get n1 squared or n2 squared is 5 squared, and whichever one is 5, the other one has to be 1, because then you get 1 squared, and you plus both of them is 25 plus 1 equal to 26. So this is how you can easily have an idea that if you choose, let's say, n1 equal to 1 and n2 equal to 5, then you have n squared is 1 squared plus 5 squared equal to 26, and this is exactly equal to the E equal to 13 E naught energy level, because there this is 26 pi squared h cut squared by 2 ml square. But what do you realize here is that you can also interchange these numbers, like n2 can also be 1 and n1 can also be 5 because they are different levels, right? But in that case also you have 5 squared plus 1 squared equal to 26 again. So this is the same energy E you are getting, 13 epsilon naught you are getting, but with a different combination of n1 and n2. So this is what they are calling twofold degeneracy, right? Because you are getting two combinations. So this is called twofold degeneracy of the energy level of equal to 13 E naught level, because you have two possible eigenstates from this problem, both of them with the same 13 epsilon naught energy. And what are those? One combination is when n1 equal to 1, n2 equal to 5. The second combination is when n1 equal to 5 and n2 equal to 1, right? So this is true that this is twofold degenerate. So in the problem it was given whether twofold degeneracy is true or not. So the answer is it is true. Okay, this is true. So let me get someone is meeting access to a person. Yeah. Right. So we have just solved up to question number 4. We move on to question number 5. So question number 5 is that suppose the second energy level of a particle in a uh, cubical box is given by E equal to 6 Eg, where Eg is the ground state energy, then the immediate third energy level will be what fold degenerate. Now you see that question number 3, 4 and 5 are interconnected, means you are basically rising your level from first you started with 1D box, right? This is the simplest one dimensional, then you went up to 2D box that we just solved, and now question number 5 involves a cubical box. So cube means it is 3D, right? So basically you are talking about a 3D particle in a box problem. This is a higher dimensional version of the same things that we have discussed in question number 3 and 4. So basically the logic remains the same, right? And we have to find out the energy eigenvalue combination and what combinations of n1, n2, and in this case there will also be a n3 because there are three dimensions here, right? So at what combination we get the energy that is given. And it is said that instead of like ground state energy is given as Eg. Now the second energy level means the next excited state to ground state basically is also given E equal to 6 Eg. Then the third energy level, that you have to find out what is the third energy level, that means the next excited state to this level. So that combination you have to find out from the n1, n2 and n3, that how many possible combinations are there for n1, n2 and n3 to get the same energy, and that will give you the answer that what will be the degeneracy fold in this case. So this is the common approach to this problem. So now we'll be solving it. Again full screen mode I'll go. Okay, so this is question number 5. So this is a 3D cubical box, a particle in a box problem but in 3D. So again because I already told you the general notion of this kind of problem is that the general energy eigenenergy value En n squared pi squared h cut squared divided by 2m l squared. Now because this is cubical, so all three directions has the same box size L, length, width and height same L and L. So this will be written down as a combination of n squared, n1 squared plus n2 squared plus n3 squared pi squared h cut squared by 2m l squared. Like treating each individual directions as a one dimensional box problem and then as a taking a combination of them. So n squared is related by this combination n1 squared plus n2 squared plus n3 squared, where each of them can take integer values from 1 to 3 etc. All of them, and independently, right? Independently they can choose these values. Now it is given that your ground state energy is Eg, and you know again we'll be making a chart because this kind of a problem needs a chart, so that someone else has entered this late. Okay, so some of you are joining pretty late to this tutorial, but anyway we are in the middle of almost in the mid of the tutorial. So this is question number 5 that we are discussing. You can catch up from here if you want. Okay, so basically we are discussing this particle in a box for 3D because you have been given a 3D box problem, cubical box problem. And as I was saying that this kind of a problem is helpful to approach if you make a chart to actually keep track of what values of n1, n2 and n3 you are taking to get what value of n. And finally based on that what will be your En. Just one second. Yeah. So, okay. Why people are joining this late? Okay, so I know all of you, many of you are joining very late, but the tutorial is from 7 to 9. So we are kind of in mid. So it is not actually possible for me to go over. But anyway, you can continue from here only. So in the 3D box problem, you have this n1, n2 and n3 as the individual quantum number for each of these directional 1D boxes, and you have to take a combination of n1, n2 and n3 to get a particular value of n and corresponding En. Okay, so let's say the easiest one is the ground state or GS. So ground state means all of them will be taking the minimum possible number, which is 1 for all of them because nothing can be 0 here. So 1, 1 and 1 means n squared is basically a linear combination. 1 squared plus 1 squared plus 1 squared is 3. So En is n squared pi squared h cut squared. So this is 3 pi squared h cut squared by 2m l squared. So this Eg that is given in the problem, ground state energy is 3 pi squared h cut squared by 2m L squared. Now the second state is basically the next excited state to ground state. Is excited state means that there is a elevation of any one of this number that will not be 1, right? But you cannot just take all of them to the next level because this is now a cubical box. So if you, let's say, how do you realize that you cannot take all of them to 2, right? Because in the ground state all of them were 1. So the simple mistake that people often do is that they take all of them to n1 equal to 2, n2 equal to 2 and n3 equal to 2 to get the next excited state. But that is wrong actually. Why? Because you have to find out the combination of n1, n2 and n3 such that it is the minimum value next to the ground state value. What I am meaning to say is that if you, let's say, take all of them as 2, okay, so what we get as n squared is 2 squared into 3 because it is 3 times it is getting summed up. So this is 4 into 3 is 12. But if you, let's say, take one of them to 2, any one of them, one of these 3 is 2 and the other 2 remains at 1. So then what you get is that 2 squared plus 1 squared plus 1 squared is 4 plus 1 plus 1 is 6, right? 4 plus 1 plus 1 is 6. So that is obviously less than 12. That means it will be giving you a n squared, or in terms of that en, because en is proportional to n squared, here en is less than this en prime, let's say. So obviously you know that if ground state is a minimum energy state, then the next energy state to ground state will be the lower energy. So you will not be jumping to this because it will be higher excited state, obviously, because this has a higher value of n squared. Rather, we'll take up one of this n value to 2 and the other 2 will remain at 1, and therefore we'll get the next excited state to ground state, which is energy wise just above the ground state energy but not like further. So in that logic, ground state can be chosen as a combination of n1 being taken as 2, n2 and n3 kept at 1. So this is 2 squared plus 1 squared plus 1 squared equal to 6. So this is 6 pi squared h cut squared by 2m L squared, right? So if that is the case, then okay, yeah, 6 pi squared h cut squared divided by 2m L squared. This is, you see that if this is your Eg or ground state energy, then the next excited state is basically 3 into 2 is 6. So this is 2 times Eg. Now the interesting thing here is that, as I said, that you can choose a combination by anything, like you can take n1 to 1, n2 as 2 and n3 as 1 again. It will also give you 6 only. You can also take these two 1 and these 1 is 2, then you also get 6. So all of them has the same energy 2 Eg with 3 different combinations of this 1, 2 and 1. So this is what I am talking about, degeneracy. So this is threefold degeneracy, but this is happening at the second state to ground state. So this is the next state that has threefold degeneracy, right? Now what will be your next excited state to the second state? So that we'll call at E2, let's say, sorry, E3. So if you call this one as E2 because it's the second state above ground state, then the third one, so I draw a line here to differentiate. This is the ground state, Eg or E1. The next state is E3, the second third state above ground state. So if ground state is considered as the level 1, then level 2 is second state, which is this energy, and level 3 is third state. So to level up one more, what we'll have to do is, now I think you have gotten the idea that you cannot take all of them to the highest value. You take one by one. So like in the last case, you took one of them to 2 and other 2 remained at 1. Now you take 2 of them to 2 and the remaining one remains at 1. Like for example, you can take first 2 as 2 and the third one as 1. So you get n squared as 2 squared plus 2 squared plus 1 squared. 4 plus 4 plus 1 is 9. Similarly, you can also take this as 1 and these two as 2. You will also get 9. And another combination is, you can take this as 2, this as 1, this as 2. Again 9. So you get this is equal to 9 pi squared h cut squared by 2ml squared. Right? So this is basically 3 times Eg, because 3 into 3 is 9. So 3 Eg. Right? So I think there has been some doubt, but anyway, to calculate the degeneracy, if you have to calculate, so the third state is, again you see there are only 3 combinations possible. You cannot go above this combination. This is the combinations that are exhausted after this. So this is also threefold degenerate for this kind of a 3D cubical box problem. So the energy level E3, or the third state after ground state, from ground state, is threefold degenerate. So what we wanted to find out is, I think the degeneracy they asked. Yeah, so the answer is, it is threefold degenerate. This is threefold. The answer is 3. But I think the mistake that you might have been wondering, that why I am writing this, they have written down the second excited state as 6 Eg, but whereas we are getting 2 Eg. That is because they have taken Eg as the ground state energy of each of the individual boxes. That means, in the case of one dimensional case, so each of the directional x, y or z individual 1D boxes ground state energy they are considering by Eg. So that is simply pi square h cut squared by 2ml squared. So by that idea, if you go, then your total ground state energy E naught becomes 3 1 squared n1 squared plus n2 squared plus n3 squared is 3. So 3 pi squared h cut squared by 2ml squared. So then that net ground state, this is the individual direction ground state. The net ground state itself becomes 3 times Eg, and from there the next excited state, that means the second state is, let's say, like we call it by E2, is basically we got 3 pi squared h squared by 2ml squared, which is 2 times E naught, but it is 6 times Eg. So that is the confusion here that you might have been wondering, but the degeneracy value we got correct. This is the notation thing that is confusing, but the degeneracy you got right, that this is 3. Okay, so this is done. Now question number 6 is about commutation relations. Finally we have moved on from the 1D box, 2D box and 3D box kind of a problem, which, as I said, is very common in these kind of quantum mechanical problem sets. So anyway, so this question number 6 is based on commutation of this quantum mechanical operators, position and momentum operator, and you have to find out that out of these 4, what is the for where you get a non-zero value of the commutation bracket. So the accepted answers are given in the option, but you have to calculate for yourself whether you are getting that value or not. So basically, yes, we'll be solving. So I'll be showing you some of these commutator bracket problems, and I think you can follow up how to take them further, because just the same rule for all of them. So this is problem number 6 on commutation. So first option you had in A is x px. So whether you have to find out whether this commutator bracket is giving you 0 value or non-zero value. So first, because they are very common canonical momentum and position operators, so they have this basic rule that their value is known standardly, so you don't even have to calculate to get them. But so this is I h cut, this is clearly non-zero, this is a non-zero value, one of these answers. But for the sake of this doing it, so I will show you how to do this in general, so that in any value except for the standard combination, if that is given to you, you can use that and solve it. So in 1D case, if you simply take this is minus IH cut uh, del x or d dx if you have only one dimension, then you this is the commutation operator, right? So it will be operating on some wave function psi. This is equal to, you have to get what happens if it operates on psi. So generally this means commutation bracket means xp commutation means xpx minus pxx, now operating on psi here. Now because they are not like simple product, they are operators, so don't confuse them and treat them like simple products. So whenever it is an operator, so it will be operated on some wave function, there has to be some wave function. So because x is a position operator, it remains on the left, and then px is minus ih ka del x, and this is directly operating on psi, so this gets d dx of psi, so this is d psi or del psi del x, right? Now the second term is a bit trickier, that you have this uh, minus I ka del x from px on the left, and then this right you have x operating on psi, which will give you simply x psi, because position operator, if it acts on some operator, it will give you back the position only. So this is x cap psi is equal to x psi. So x psi is now becomes the whole thing that this momentum operator will be operating on. So now this is minus ih cut. Now this derivative is independent, so you just take x d psi dx minus plus ih cut. Now del x of psi into x, how what that gives you is that first derivative on x keeping psi independent is simply psi, plus keeping x independent and derivative on psi is psi prime d psi dx. So what you get is that minus ih cut x psi prime plus ih cut psi plus ih cut x psi prime, where psi prime is d psi dx. So this cancels out and you get simply ih cut psi. So finally you get that x px operated on psi is equal to ih cut psi. From there you can see that this operator commutation relation is x px equal to ih cut, which is non-zero. So this is the basic idea how to do these sorts of things. So if you look up the other options that is given to in this problem is what is x py. So definitely even before calculating it, you should know that this should give you 0, because one is x and the other is y directional. So naturally derivative of y will be giving you zeros on that. So this is this is commutative basically. Even if you sometime get this kind of a thing that y px, you blindly say 0, because they are from different directions. So you have to, at least to expect that you will get a non-zero value, you first have to ensure that all of them are in the same direction. Let's say all of them are x or all of them in terms of y. If you take a difference, then directly say that this is 0. But the problems that both of them are x, then you specifically need to calculate, or some cases like this you have a standard form that is basically generally people remember. But the other options, like they have x squared px, so this you may not remember or may remember, but I'll tell you that the solution is similar. How you solve this, just instead of x, treat it with x squared and you will get the thing. So let's say this will be as x squared px minus px x squared operating. Always you have to, this is not all, because this is the operator problem, always try starting with the operator that will be starting with a wave function where on which the operator will be acting on, and then put the values in separately, like px equal to minus ih del x, like that, and then treat the whole formation. So this I'll not solve for this, you can check for yourself, but I'll tell you the answer, that it is 2ih cut psi. So basically if you operate this whole thing, if you solve out, so you will get that this is equal to 2ih cut psi, 2ih cut x psi. So that is why this is this. Okay, so this is also non-zero, right? And basically non-zero. So yeah, So the other option I'll be maybe solving for one of these to you is basically x px squared. How much is this? So if this acts on psi, then this x px squared minus px squared x psi. Now because px is minus I h cut del x, so px squared will be minus I h cut whole square. So I squared is minus 1 and h squared is h squared, and this is del 2 del x2. So this is minus x cut square del 2 del x2 minus minus plus h cut square del 2 del x2 x on psi. So x on psi operator will be giving you x psi only. So this is minus x h cut square d2 psi dx2 plus h cut square d2 psi dx2 operating on the whole x times psi, because x has operated on psi and given you x psi. So this is minus h cut square x psi double prime, because this is double derivative on psi, plus h cut squared x psi prime. So you take one derivative first, so d dx, one derivative on x psi is x psi prime plus psi, right? Then you take the second derivative is h cut squared, this is psi prime plus x psi double prime plus psi prime. So this is minus h cut square x psi double prime plus h cut square x psi double prime plus 2 h cut square psi prime. So these two cancels out, so you get 2 h cut square psi prime. But think of it this like this, that this is psi prime and not psi. So you cannot further conclude that you have gotten the value of psi x px squared, because there you have a psi here. So you have to somehow take it back to the form of psi, and how to do that is basically you have to write down psi prime in terms of psi. So this is psi prime is d psi dx, and if you check you will see that this can be written as I by h cut px times psi. Why? Because you just put the value of px, this is minus I h cut d dx on psi. So this h cut and h cut cancels out, minus I squared is plus 1. So this is simply d psi dx or psi prime. So you see that this can be written like this, where you have expressed it in terms of psi. So this becomes 2I h cut squared by h cut px psi, which is basically 2I h cut px psi. Now we have been reduced to the expression of psi. So you take separately the psi part, and you are only left with x px squared is equal to 2I h cut px, which is again non-zero. So the answer will be, the non-zero commutation brackets will be this term, and the first term. Only the b will be zero commutation. So let us choose the answer. So only non-zero commutation will be all three, this and this, A, C and D. Only B is 0. Okay. So we have solved already 6 problems, 4 more are left. So quickly doing that, question number 7 is, particle is represented at time t equal to 0 by the wave function psi x comma 0 is basically t equal to 0, where this kind of a thing is given. Okay, and these are constants that are unknown. A normalization constant A you have to find out. So whenever this kind of a problem is given, that there is a wave function and normalization is mentioned, so you know that wave functions, quantum mechanical wave functions, has this property of normalization. That means it is always it should be a normalized wave function to take the total probability to 1. So that is basically true for all. So by keeping that in mind, you know that the total probability is basically the amplitude whole square. In this case, the amplitude is the wave function. So that means for normalization to be true, which is valid for all the wave functions quantum mechanics, normalized wave functions is minus physical wave function should be normalized. So psi x whole mod square dx from plus infinity to minus infinity integral will be equal to 1. That is a condition from normalization. So in this case, we have this psi x expression and we will be using the normalization condition to get the value of the normalization coefficient a. So this is problem number 7. Right. Problem number 7 is that, as I said, that minus infinity to plus infinity psi x comma 0 is given to you, this whole mod square dx equal to 1. Okay, normalization condition. Now you put the value of psi x 0, as it is mentioned in the problem that psi x 0 has only finite value between minus a to plus a, and elsewhere it is 0. So there is no point taking the limit from minus infinity to plus infinity, because only in this bound of minus a to plus a it will have a non-zero value. So we change the limit to minus a to plus a and put the value there, where psi x comma 0 is a squared minus x squared. So this whole squared will be a squared, x squared minus x squared whole squared dx equal to 1. Now you simply do the derivative, the integral. So you first break down this squared. So this is a to the power 4 plus x to the power 4 minus 2a squared x squared dx equal to 1. A squared is constant, comes out. So this is, if you integrate, this is a4x plus x to the power 5 by 5 minus 2a squared x cube by 3. And so first of all, you can simplify this even further, that because it is all even function in x, okay, so your integral limit can be taken from minus a to plus a is similar as 2 from 0 to a, because this is symmetric with x. Sign dependence is not there because x only even power is there, right? So this will simplify the limit a bit, that this is 2a squared. Now the integral limit is 0 to a. Okay, just give me a minute. Just one second. Let me quickly finish this because I have something else to do. So 2a squared 0 to a is e to the power 4 x, e to the power 4. So integral will be written plus x to the power 4 minus 2a squared x squared dx equal to 1. Now you solve the integral. This is 2a squared e to the power 4x plus x to the power 5 by 5 minus 2a square x cube by 3. This is taken from 0 to a equal to 1. Now because 0 will be all 0 terms, so you just get the value of the upper limit a to the power 5 plus a to the power 5 by 5 minus 2 a to the power 5 by 3 equal to 1. This is 2a squared into a to the power 5 taken as common. This is denominator is 15, so this is plus 15 plus 3 minus 10 equal to 1. So you get 2a squared into 8 by 50 equal to 1 a to the power 5. So a equal to 15 by 16 a to the power 5 square root. So this is the normalization constant value, right? So let us check whether that is in the option. Yeah, that is in the option. So 15 by 16 to the power 5 is this, right? So this is the problem. Question number C is the correct answer. Now question number 8 is the wave function of a particle in a 2D square box, again a 2D square box thing, of length L at time t equal to 0 is given by this. Okay, so there is no time involved in any of the terms here. Now the wave function at time t can be written as what expression? So there is a very simple trick that you have to use in this kind of problems, is that whenever you have a wave function at t equal to 0, let's say psi x 0, and you have to get what is psi x at t. So basically time only introduces an additional phase factor to it, which is basically psi x 0 e to the power of minus I et by h cut. So this is the additional phase factor that comes due to time. Okay, so you only have to calculate this thing and you will be getting your psi xt. And to calculate this, all of this is known, only the eigenvalue you have to note down. Eigenvalue you have to calculate, and then you put that and get this value. So let's say for this case, question number 8 I'll solve here only, because not be a very long problem. So you see that this is a 2D square box problem, and the eigen functions, you see a linear combination written as phi 1 2 or 2 1. So this is basically twofold degenerate because n1 and n2. So you see that this is a second state from ground state. So n1 is 1 2, or this is 2 1. Ground state will be both of them 1. So this is the second state. So n squared is 2 squared plus 1, which is 5 for both of them, right? So then En is equal to, because n squared is equal to, as you remember, n1 squared plus n2 squared, then En is equal to n squared pi squared h cut squared by 2ml squared. So this is 5 pi squared h cut squared by 2ml squared. So here you just put that value and you get that psi xy at t will be psi xy at t equal to 0 times e to the power of minus I 5 pi squared h cut squared into t by 2ml squared into h cut, right? So h cut can cancel out, and basically psi xy t equal to 0 you already have. So this term that is given in the question, this thing will be there into e to the power of minus I 5 pi squared minus IET by h cut should be there. So this h cut and h cut square should cancel out each other. So this h cut t by 2ml square. So I think there is a typing mistake, that here this problem is, this option is the closest match. So this is the psi x y t equal to 0, like I have written down here, multiplied by this phase factor is exactly same as this 5 is similar to us. Only thing is that they have not cancelled out this h cut. This h cut square should possibly be h cut, or sometimes this can also be taken as 1. So instead of that you can just take the closest match as h, this option number D. Okay, so now question number 9. The normalized wave function of a particle is psi x equal to this thing, where capital A and B are constants. Then the uncertainty in its momentum is how much? So momentum uncertainty is delta P, which is nothing but P squared average minus P average whole squared and its square root. So you have to get these values from the momentum operator operating on psi. You will get these values, and then by calculating you can get this delta P. So how to do that? Let us now solve this. So question 9. Question 9 is on, so delta P whole squared is P operator squared, then its average, minus P operator average whole squared. So P, you know that this is minus I h cut d dx in when you are thinking about one dimension x. So what is P average? P average is basically operator average is taken as like this. So this is the bracket notation. I think you have not been familiar to this, because this is, I think, later in the course, I don't know. But the integral representation is that whenever you have to take some expectation value, this is set. So this bracket means this expectation value, right? So to calculate expectation value, the idea is that you have to get the wave function, the eigen function, and you take the psi star, that is the complex conjugate of that, then the operator sandwiched in between, which is the P operator in this case, and then the actual not complex conjugate, the actual original wave function, and take it from minus infinity to plus infinity. So this is the expectation value formula. So like here, this is psi star, this is minus I h cut, d dx will be d psi dx. So this is dx minus infinity to plus infinity, right? So now you have this psi given to you as, I think, a e to the power of, what was that, a to the power of iax minus ibt. iax minus ibt. So then psi prime is d psi dx equal to a ia to the power of iax minus ibt. Only x derivative is taken, so ia is there. So this is minus ih cut a into ia. So and then psi star, then so this a and e to the power ia bt is actually giving you another psi back, right? So this is, let's take it as psi only. So there is no a here, only minus ih cut and ia comes out, and psi star psi dx in minus infinity to plus infinity. So this is minus I squared is plus 1, so this is a h cut, and this is normalized wave function, so this value is always 1. So this is basically mod psi whole square, right? Mod psi whole square is psi star psi, because it is a quantum mechanical wave function, so complex conjugate has to be multiplied. So this is basically a h cut, right? One value is obtained, and in the expectation value of the square of the momentum operator is how much? This is again sandwich it between psi star and psi. This is the formula, and p is minus I h cut d dx, so p squared is minus h cut squared d2 dx2. So here p squared psi is minus h cut square psi double prime x, because it is double derivative on psi. So minus h cut square d dx of first psi is d2 dx2 of a to the power of I ax minus bt, right? So the first psi prime we already have, so you don't need to calculate again. Psi prime is ia psi, right? So this is basically minus h cut square d dx of psi prime, which is ia psi. So ia comes out minus ia h cut square d dx of psi. Okay, minus ia h cut square. Again psi prime is ia psi. So this is minus and minus, this minus I squared is plus 1, so a squared h cut square psi. So you keep it, place it here. So this is psi star a square h cut square psi dx from minus to plus infinity. Now because these are constant terms, so it comes out, so only mod psi whole mod square dx. This is normalized, so this is 1. So this is simply a squared h cut square. Now you have the error in our uncertainty value delta p squared is equal to p squared average minus p average whole square. But p squared average is this, a squared h cut square, minus p expectation value or average is a h cut. So a h cut whole square is again it's a square h cut square, which is 0. So the error or uncertainty in momentum is 0. So this is done. So we have obtained the answer. This is 0, right? This is 0. Now the last question is, suppose in a double slit experiment, the waves emitted by slit 1 and 2 are psi 1 R2 RT and psi 2 RT respectively. Then the intensity produced on the screen when both the slits are open is given by individual psi 1 whole mod square plus psi 2 whole mod square. So this statement is true or false. Obviously this will be false, because this is a basic idea of difference between classical and quantum. Because whenever you are talking about this quantum interference of or dealing with wave functions that are quantum in idea. Then in the double slit experiment, if both of the slits are open, so both of them has some psi 1, individually psi 1 and psi 2, but when both of them interfere, so because of the interference there will be some terms that are coupled terms of both of them, like let's say net psi is equal to psi 1 plus psi 2, right? So net probability of this coming out, or intensity, whatever you want to say, intensity is actually amplitude whole mod square. So in this case psi whole mod square, which is psi 1 plus psi 2 whole mod square. Now this will be psi 1 whole mod square, so this will be not be like a simple a plus b whole square, but because they are quantum mechanical wave functions, so psi 1 whole mod square plus psi 2 whole mod square, and then there will be coupling terms like psi 1 star psi 2 plus psi 2 star psi 1. Now these terms come because of the interference of waves from individual slits, and for quantum mechanical sense this interference term is not equal to 0. But if you only deal with a classical idea, then only classical probability or intensity is this much, that the individual intensity summed up is the net intensity. But quantum mechanically this is not correct, because always there will be some interference between the terms from individual components, and so the net probability is not the independent probability summed up, but there will be coupling terms, so this is false. Okay, so with this we have solved all 10 problems. So I'll ask that whether you have a doubt in any of these problems that I have solved, then you can let me know now. If not, then we can finish this session maybe. And we meet next week, and the time is 7 to 9. So some of you have joined pretty late, so I was already in middle of solving. So I don't know whether you have able to catch up or not. But there'll be anyway, this session I'll be also putting on a recording, so you can check it out from there and match with your solutions in your time. Okay, so any questions from any of you? Um, so I assume that there is no questions. So then we stop the class for today here only, and we'll meet next week Saturday. Okay, so you have a question?
Ma'am, some book is there, madam. Which book can we follow for
Like
problems alone?
for problems, for basic level you can follow this, for basic level understanding and especially problem solving, Griffiths
Oh,
is very good. Griffiths quantum mechanics. Then H.C. Verma quantum physics book is a general book, but that has like pretty good example problems and solutions, so you can
okay,
look it up.
Griffiths, okay. One is Griffiths, next, other ones?
Griffiths, and another is H.C. Verma. H.C. Verma quantum physics
Oh,
or
it's,
quantum mechanics, I
okay,
forgot the name, but it is a red colored book cover.
okay.
Griffiths is a standard book for beginning level, but beginning level I'd also suggest AC Verma for like understanding of the problems, because they have like solve problems as well. Griffiths also you get solved problems, so that will give you an idea.
Thank you very much, madam.
Okay. Okay, so no questions then further, so we stop here and we meet next week. All right.